Most people step right over the very stones they chase at gem shows. Along foot-worn creekside trails or inside shallow bends where water slows and deposits heavier sediments, there are moments when sunlight strikes just right, and a deep red or blue glint peaks from otherwise dull gravel. Not glassy, not metallic, just dense, slightly waxy luster with color that persists even under shadow. These are the silent first signals of raw corundum, sapphire or ruby, hiding among the ordinary. The deceptive part? Most of these fragments are opaque, embedded in host rock, or coated with iron oxide. Nothing about them screams gem. They're often tucked in matrix quartzite or marble, showing only a fingernail-sized window of color. That's why initial identification depends more on observation than expectation. The natural tendency is to seek transparent crystals, but high-grade ruby and sapphire often begin as cloudy, fractured, or even heavily included nodules. What separates them at this early stage is how they interact with light. Not in brilliance, but in resilience. That deep body color under diffuse daylight is rarely matched by other minerals in the same environment. Creeks running through metamorphic terrains, especially those with marble, schist, or gneiss, tend to host this kind of gravel. Think of places where mountain runoff scrapes across old metamorphic belts, especially those intersected by ancient fault zones or pegmatite dikes. These fractures often act as vertical elevators for mineral-rich fluids that solidified under heat and pressure long before erosion set them free. Over centuries, fragments of corundum weather loose and travel downstream, sometimes just meters, sometimes kilometers, until the water slows and they drop into the gravel bar. What gives these stones away is subtle. Their surfaces often resist wear better than surrounding material, leading to smooth but stubbornly angular forms. They may hold sharp edges even after long creek transport, unlike quartz or feldspar which round off quickly. And while most rocks in the mix reflect a dull gray or tan, corundum's color, when visible, is internal. It glows dimly rather than shines, and it doesn't shift with angle. Rubies in particular tend toward a dense, cherry-like red with hints of violet or purplish undertone, while sapphires can appear steely blue or inky, almost black, until wet. But if a stone like that catches your eye once, it deserves a second look. Because in a handful of gravel, only one piece might be corundum, but that single fragment, properly tested, could be worth weeks of effort. The next step, though, is not to pocket and go, but to examine what made it visible, and why most other searchers missed it. Because if you found one, there may be more upstream, just one test away. A raw sapphire or ruby often won't show its full color until cut. But before a single facet is revealed, the stone already broadcasts its identity through resistance and density. Long before a flame test or lab submission, the hands and eyes of a practiced searcher can narrow down candidates using just touch, scratch, and balance. Among 100 creek stones, a piece of corundum resists more than the others. Resists being scratched, resists tumbling into roundness, and even resists the hand's instinct to dismiss it. The key is this. Corundum ranks 9 on the Mohs hardness scale, second only to diamond. This means it will easily scratch quartz 7, glass 5.5, and almost anything else likely to share its environment. When you drag an uncut piece of ruby or sapphire across the surface of a clear quartz pebble, or even a simple bottle bottom, it should leave a clear groove. The reverse should not happen. Most field testers use either quartz or a strip of silicon carbide sandpaper, Mohs 9, to check quickly. If the suspect stone shows no scratch while quartz crumbles under it, you're looking at something unusual. Weight tells its own story. Corundum is denser than most common rocks. At roughly 3.9 to 4.1 g/cm superscript 3, it's significantly heavier in hand than quartz, 2.65, or feldspar, 2.5 to 2.7, both common in creek gravels. This heft isn't obvious in isolation, but in side-by-side comparisons, you can feel it. Two stones the same size will feel notably different in weight, and this weight-in-hand test, while subjective, is one of the oldest and most reliable ways prospectors first suspect corundum. Over time, you'll recognize the feel without needing scales. Shape and fracture also assist. While corundum rarely forms clean crystals in secondary deposits, it often retains hints of hexagonal habit or barrel-like edges, especially in sapphire. Broken faces tend to be conchoidal, but with a subtle grease-like sheen. Rubies, especially those from marble-hosted zones, may show tabular or spindle shapes, sometimes locked in matrix. Even if the color is faint or concealed, the structural integrity of the piece, the way it resists breaking, the edges that remain crisp, contrasts sharply with more fragile or weathered companions. These tactile and mechanical cues are not just academic, they're practical triage. In the field, you don't have time to analyze every pebble. The hardness and weight tests help isolate the most promising candidates in minutes, long before you ever wash them or view them wet. And while a glassy red fragment might tempt you, if it scratches easily, it's out. If it crumbles under your nail, move on. The real stones don't flinch. Still, these tests aren't enough alone. Some spinels and garnets, common in the same environments, can mimic the feel and color. That's why the next step isn't confirmation, but context. Figuring out where the rock came from and what mineral clues traveled with it. Because if you've got true corundum in hand, the ground nearby is likely whispering the same message, just in a different language. Not every stream holds promise, no matter how colorful its stones. The real difference lies deep beneath the terrain's geologic ancestry. Raw rubies and sapphires form under immense pressure and heat, typically in metamorphic environments, but only become accessible when exposed through weathering and erosion. What matters is not just where they formed, but where they're being released. And that means watching for the overlap between old metamorphic belts and modern erosion dynamics. Corundum forms primarily in two contexts: aluminum-rich metamorphic rocks like marble and gneiss, and aluminous pegmatites or cyanite intrusions. In both cases, the surrounding environment must lack silica, because too much silica causes aluminum to bond into other minerals like feldspar or sillimanite. For rubies especially, marble-hosted zones, often in contact with dolomitic limestone that has been subjected to regional metamorphism, are ideal. Sapphires, on the other hand, appear more frequently in gneissic terrains or within cyanitic bodies that have undergone alteration. From a field perspective, you're looking for areas with known outcrops of schist, marble, or gneiss, especially where folding or faulting has exposed deeper layers. These zones often appear in old orogenic belts, such as the Appalachian Mountains, US, the Mogok Belt, Myanmar, or parts of Madagascar and Sri Lanka. In North America, look for zones of known amphibolite or granulite facies metamorphism, as well as regions with historic bauxite or kyanite mining. Both signal aluminum-rich environments where corundum may co-occur. However, high-grade metamorphic bedrock alone is not enough. The sweet spot arises where these formations are actively eroding into creek systems, especially on slopes or where a mountain stream crosses contact zones between lithologies. Sapphires and rubies, due to their hardness and chemical stability, resist weathering better than most minerals. This means they accumulate downstream from their source over centuries, especially in traps like inner river bends, plunge pools, and behind natural rock riffles. Elevation changes also matter. A gently sloped gradient allows heavier material like corundum to settle, rather than being flushed too far downstream. Trails that cross below talus slopes, ancient terraces, or secondary alluvial fans often hold float from higher, mineral-rich elevations. In places with periodic flooding, older material can become reworked into new surface layers, making even well-trodden trails worth rechecking after major rain events. Ultimately, It's the convergence of three forces that makes a site valuable. 1. The presence of corundum-bearing bedrock. 2. A mechanism for physical release, faulting, freeze-thaw, slope failure. And 3. A creek or runoff pattern that concentrates those pieces in a retrievable layer. These aren't always in obvious places. Some of the best finds have occurred in small feeder creeks or dry gullies that only flow after seasonal rain, rather than large year-round rivers. Before digging or panning, study topographic maps and regional geologic surveys. Overlay fault lines with known marble belts or aluminous formations. Look for old mica or talc quarries. These often occur in the same metamorphic conditions favorable to ruby and sapphire. If you can pinpoint where these variables overlap on the ground, you're not just hoping, you're prospecting with precision. And the next clues in the gravel may already be waiting. Before you ever spot a ruby or sapphire in the pan, the surrounding minerals may already be pointing straight at it. These aren't just visual companions. They're geological fingerprints left behind by the same metamorphic or magmatic forces that formed corundum. Recognizing these indicator minerals in trail cuts, creek gravels, or erosion faces can save hours of guesswork and signal when a site deserves serious attention. 3 major indicators stand out: kyanite, garnet, and rutile. Each forms under similar high pressure, high temperature conditions, and tends to concentrate in the same erosional pathways as corundum. Their presence doesn't guarantee ruby or sapphire, but their absence makes it less likely. Kyanite is a key telltale in aluminum-rich metamorphic zones. It appears in long, bladed crystals, often blue but sometimes white or gray, with a pearly to vitreous luster. While not heavy, kyanite's unique cross-splitting cleavage makes it recognizable when broken. Importantly, it often forms in the same conditions that produce ruby and marble, particularly in regions where clay-rich sediments were metamorphosed into schist or gneiss. If kyanite shows up in stream gravel, it means you're close to the kind of aluminum-saturated metamorphic source that can host ruby or blue sapphire. Garnet, especially the almandine variety, shows up more frequently but still carries meaning. These deep red to brownish stones are dodecahedral in habit and often mistaken for ruby by the untrained eye. But their lower hardness, 6.5 to 7.5, and slightly glacial luster make them easy to dismiss with scratch or density testing. Still, a high volume of garnet in a creek is often associated with high-grade metamorphism. Where you find garnet, there's potential for corundum to occur nearby, particularly in zones where biotite or hornblende schists intersect with marble. Rutile offers a more specific and exciting clue. These tiny, metallic-looking needles or grains, often reddish-brown or golden, can either be present in the host rock or as inclusions within corundum itself. Star rubies and sapphires, prized for their asterism, owe that optical effect to aligned rutile needles. If rutile grains are present in panned concentrates, especially in the same size class as denser materials, it's worth a closer look. Their high specific gravity, 4.2, 4.3, means they tend to settle where corundum would as well. Other helpful, though less definitive, co-indicators include chlorite, staurolite, and sillimanite. These minerals appear in high-grade metamorphic assemblages and can signal a fertile mineralogical environment. In particular, staurolite, identified by its characteristic cross-shaped twin habit, often coexists with garnet and kyanite in mica schists, forming a triangle of conditions conducive to ruby. But context is key. The indicators only matter if they're part of the heavy fraction, the portion of gravel that resists water flow and settles in traps. When you find a concentration of garnet sand, with occasional kyanite blades and flecks of rutile, you're looking at the remains of a very specific geological puzzle. And if you've already tested one of those grains and confirmed it's corundum, then these indicators aren't just supportive, they're directional. Use them to trace upstream, map zones, or decide where to deploy heavier tools. Because each of these minerals doesn't just suggest possibility, they hint at a system. And systems, once found, can yield not just a stone, but a pattern. The next step? Sorting that pattern with your eyes and fingers, without yet picking up a pan, before a single drop of water touches the stone, before you lose it in the pan or over-test and damage a specimen. The dry screening phase sets the tone. With just your eyes and hands and no specialized gear, you can reject 90% of gravel and isolate the tiny percentage that might be raw sapphire or ruby. The key lies in noticing what doesn't quite fit. A texture too smooth, a luster too dull yet dense, or an edge too sharp after miles of tumbling. Begin by spreading your scoop or handful of dry creek gravel onto a flat, shaded surface. Ideally a neutral background like a piece of cardboard or pale cloth. Direct sun often creates glare that hides the subtle clues. What you're looking for isn't brilliance or sparkle, but a muted, waxy or subadamantine luster. Somewhere between greasy and glassy. Most quartz or feldspar pieces will appear bright and reflective. True corundum, even when clouded or included, reflects light more diffusely, almost like a matte gemstone that holds color deep inside rather than bouncing it back. Next comes translucency. Hold candidates up to the sky or a backlight, edge on. Many sapphires and rubies in the rough are not transparent, but show clear translucence along the thinner margins. A deep red ruby might look nearly black in bulk, but allow cherry-colored light through the thinner edges. Sapphires may seem inky blue until light exposes faint banding or zoning within. Most imposters, garnet, basalt, dyed quartz, will either transmit too much light or none at all. Shape also offers guidance. In secondary environments like creeks and trails, full crystals are rare, but corundum often retains fragments of its hexagonal habit. Flat ends, barrel-like sides, or angular chips with unnatural symmetry. You may spot a subtle taper or flattened face inconsistent with the rounded contours of quartz river stones. Also, corundum resists abrasion. If a candidate maintains an edge or facet despite surrounding erosion, take note. If your location shows visible iron staining, common in rubies hosted in marble or iron-rich schist, watch for stones with hematite streaks or rusty coatings. These can obscure the color, but not the structure. Rubbing lightly with a dry cloth or edge of cardboard can remove just enough surface grime to reveal key traits without wetting. It's easy at this stage to get excited about red or blue glassy pebbles, but remember, color is the least reliable cue. Dyed quartz, slag glass, or weathered garnet can mimic the hues. Instead, focus on what's resistant. Surfaces that shrug off scratches, edges that haven't smoothed, colors that don't shift under changing light. This dry pass doesn't confirm a ruby or sapphire, but it eliminates distractions. What remains after this sort are the true candidates worth testing. They're not shiny, they're not perfect, but they hold just enough contradiction, weight, translucency, form, to deserve the next stage, contact testing. And that's when clarity, both optical and diagnostic, really begins to emerge. Even among carefully screened stones, visual indicators aren't enough. Rubies and sapphires must prove themselves under pressure. Literally, their defining trait, a Mohs hardness of 9, provides a decisive way to separate them from pretenders like quartz 7, feldspar 6, or garnet 6.5 to 7.5. And in the field, with only basic tools, this becomes your fastest, most revealing test. Start with the simplest scratch sequence. Carry a piece of quartz, natural or tumbled, and a small tile or square of silicon carbide sandpaper, commonly rated around Mohs 9, easily sourced from hardware stores. Select your candidate stone and, using firm, even pressure, try to scratch the quartz surface. If it leaves a distinct groove, not just a rub mark, you may have corundum. Flip the process. Drag a known quartz pebble across your candidate. If the suspect stone shows damage or dulling, it's out. This reciprocal method avoids over-relying on one material's wear alone. A true corundum specimen will not be scratched by quartz, knife blades, typically 5.5, or even hardened steel. If you have a multi-tool or steel file, attempt to carve a notch. Real corundum resists everything except diamond and certain carbides. To test more precisely, apply your candidate to silicon carbide sandpaper using consistent strokes. A non-corundum stone will rapidly lose its edge or begin to powder. Corundum, even rough and uncut, will leave the paper intact or slightly polished without degrading. Just remember, use a corner or inconspicuous edge. Testing too aggressively on a high-potential sample could reduce value. Another field trick: try to scratch a clean window in a bottle, ceramic mug bottom, or tempered glass. Most glass is around Mohs 5.5 to 6.5. A corundum stone should carve into it easily. Watch the scratch under light. A groove with raised edges indicates a cut, not just a mark. But there's a caveat. Some garnets and spinels approach the lower edge of corundum's hardness and can briefly seem to pass. That's why this test must be used in concert with your earlier observations: weight, luster, and translucency. The goal here is not final identification, but to narrow the field further, cutting through ambiguity with a direct, tactile challenge. Hardness, above all, is the corundum fingerprint. It can't be dyed, coated, or faked in a natural setting. And while lab stones or synthetics can match the rating, nothing mimics the feel of real, ancient ruby or sapphire, resisting every test you throw at it. Up next, what to do with the pieces that pass this trial, and how black sand could either betray or confirm the next step in your find.